webinar of the SASIP webinar series. Today we have Tobias Finn, who is one of our postdoc in SASIP. In particular, Tobias work in WP4, which is the working package dedicated primarily to developing advanced data simulation and machine learning methods. Tobias worked in a group of Marc Bouquet in Paris, together with Charlotte and Alban, and also broadly with other people in WP4. Tobias has done his PhD in Hamburg, and I think his first area of work was data simulation, but he told me that he was already in love with machine learning while this name was not so popular as it is now. So in a way, it has not only a background in data simulation, which is of course a very good background for someone who wants to work in machine learning, but also on top of that, he was already in love with the discipline from long ago. In WP4, he has been working on a number of problems dedicated to the use of advanced machine learning for the Arctic sea ice. On the one side, he worked on developing a correction for the subgrid scale learned using machine learning, and more recently, he has been working on the use of diffusion model and generative models, which is what he will talk about today. So Tobias, the floor is yours. And of course, to everyone, we will have a question at the end, but if you want, you can just start piling your question in the chat, and then I will moderate it afterward.
Yeah, you can actually also ask questions in between.
Okay, okay, yeah, perfect. Okay, that's okay. Good.
I like it much more interactive, so. Yeah, thank you, Alberto. Yes, as Alberto has already said, I will speak about my recent work on using generative diffusion models for CS models. And so I will not really speak about geophysical modeling, but really about data-driven modeling and how we can learn these data-driven models with generative deep learning and the nice features about it. So you may now ask, why generative modeling? And so there was a recent trend in the last 2 to 3 years in generative modeling, which has revolutionized image generation. And so previously, before diffusion models became a trend, so-called generative adversarial networks were the hottest topics in generating images. But then so this paper is from 2021, and since then diffusion models are basically the way to go to generate images. And so as you can see, OpenAI develops diffusion models. Also Google develops diffusion models. And so these models can now generate images that look very, very realistic. And this image looks even hilarious because, I mean, a panda baking is not really realistic. I mean, it looks realistic, but it's for sure not a true image. And then 1 or 2 months ago, there was also a new paper which was called Video Generation Models as World Simulators, again from OpenAI. So from one of the big companies, and actually they presented a proprietary video generation based on diffusion models, which can generate videos that look basically like a real video, and these videos are now up to 1 minute. So this means deep learning is now able to generate realistic looking videos up to 1 minute. And so this is what I call, or also others call, the revolution of generative computer vision. And my personal take is that this will also happen soon for geophysical modeling. And yeah, I hope I will show you some evidence why I think so. So the main idea is to use this generative revolution for CS modeling. And here I will now focus on surrogate modeling. So this means really on completely data-driven models without any physical component. And instead of learning it from observations or something like this, I will here show surrogate models that are learned as emulator of a geophysical CS. Here specifically the Lagrangian version of neXtSIM. Why do we want this? First of all, if we have such an emulator, we would have a faster version of our model, which can be an advantage, for example, for climate projections. Then second of all, we would have the adjoint for variational data assimilation, basically for free, because the surrogate model is completely auto-differentiable, and so this means that we can get the adjoint for variational data assimilation. And then third, we can cycle the emulator together with data assimilation to learn basically the model from observations and to go then even beyond what the geophysical model would say. Now let's do this step by step. So I will slowly build up everything. And yeah. So the first thing we need is for sure data. So we need data, we need a lot of data. And what I use as data is our simulations from our state-of-the-art CS model. So I use the simulations from Guillaume, done with the Lagrangian version of neXtSIM in a full Arctic configuration. And neXtSIM is in these simulations coupled to the ocean component of NEMO. And instead of trying to model the whole Arctic, I just try to model a small region, which is here depicted by this red rectangle. And so I then basically extract this region. And this region has 64 times 64 grid points. And I basically don't impose any literal boundary conditions for this region. So the task is then we have our data. So we have the data here is the sea ice thickness, the sea ice concentration, the damage, and the velocities in x and y direction. So the two velocity components. And our task is so the surrogate model should take the initial conditions and simply output the sea ice thickness, sea ice concentration, damage, the u and v velocity 12 hours later. And instead of just using the initial conditions, we also use forcings from arrow 5. Here I restrict the model to just 4 different forcings for time 0 and time plus 12 hours. So the forcings are the 2 meter temperature, the 2 meter humidity, and the wind speeds or the wind velocities in 10 meters height. And so based on this, we want then to train the surrogate model. The data is there are in total 20, how many years are there actually? 24 years of data. So I use the first 20 years of data for training, then 2015, the complete year 2015 as validation data, and 2016 to 2018 as testing data. So this means I will train the neural networks on the training data. Then I will select the best performing model on the validation data, and all the results that I will show are based on the testing. And then to increase the amount of data, I also do so-called data augmentation. So this means during training, I randomly flip my data in the horizontal and vertical direction, and I additionally randomly rotate my data. So which means I have a switch if the data should be rotated by 90 degrees or not. And this then basically artificially increases my data amount. And and I have basically seen that this is necessary to get nice results. Or it is not necessary, but one can get nicer results with it. So the next step is then if we have all this data, if we have processed all this data into a nice format, we have to build the surrogate model. And first, we have to select a neural network architecture. So I use some sort of let's say fancy neural network architecture because I use a so-called unit. So a unit is a neural network architecture that is normally based on so-called convolutional layers, so on layers that move through the data, through the fields. And I combine this with a so-called vision transformer. So I have convolutional layers that basically don't scale my data. I then apply so-called transformer blocks. So these are specific blocks that have so-called self-attention included, but it is not so important here. And then I use again convolutional layers to scale up again to my original data. And in total, the neural network has 7.6 million parameters, which is quite big already. Yes. And then the first thing we will do is we will train the model as deterministic model. So what I mean by this is assume we have our initial conditions here visualized by this dot. We have our target data in some space, and then we train the neural network by assuming a mean squared error loss. So by making basically a local Gaussian assumption, and then the neural network is basically trained to minimize the mean squared error loss, which means that the neural network outputs basically the mean of an assumed Gaussian assumption. So if we do this, again, we train the neural network for 12-hour lead time, and then we can apply by cycling the neural network, we can apply the neural network for as long as we want. So here I will show no results for lead times up to 15 days. And so this is the normalized group mean squared error, and this is the normalized group mean squared error over all 5 state variables. So over the thickness, concentration, damage, and the velocities in X and Y direction. And so first of all, we need some baseline methods. So the first baseline we have chosen, or I've chosen, is the so-called persistence forecast, where we basically predict the initial conditions all over for all lead times. And then and the second baseline is a so-called free drift model. So based on simplified equations, we can derive that the velocities, that the CS velocities are proportional to the velocities in the atmosphere. And then based on this, we can then advect the tracer variables, so the CS thickness, CS concentration, and CS damage with this estimated velocity, and this gives us a so-called free drift model, or it can be also called Lagrangian persistence model because it affects the fields. And so we can see that the free drift model performs much better than the persistence forecast, and which is already in some sense nice. And so if we now use our deterministic surrogate model, we do even better. So our deterministic surrogate model performs better than the persistence forecast than the free drift model. Yes, and this holds actually for all variables. So even for the CS velocities up to the tested 15 days. So this means that this neural network works. However, I wouldn't be here if there isn't a problem. And so if we dig a bit into the results, so here I show the CS thickness for 12-hour lead time, for 7-day lead time, and for a 50-day lead time. And so this is for neXtSIM, so our targeted simulations. And now if we do this with our deterministic model, we can actually see that the deterministic model matches the general structure after 7 days, but we can already see quite some smoothing. And then after 50 days, we can even see that the deterministic model produces artificial strains, artificial patterns, which are not in the data. And so this basically indicates that the deterministic model is in some sense a bit unphysical and leads to a smoothing. And so we can also see this if we estimate the energy spectrum. So this measures how much energies in the different scales of the CS thickness are included. And so the black line is what neXtSIM sees, and the blue line is what the deterministic model sees after a 15-day forecast. And we can clearly see that the energy in the small scales is much lower than the energy in the large scales. The energy in the small scales of the deterministic model is lower than the energy in neXtSIM for the small scales, whereas for the large scales, they match pretty good. So this means that the deterministic model somehow smooths out the fields, and now comes the twist. This is basically also what Charlotte has seen in her emulator, in her recent work, that if you emulate the CS thickness only, you get pretty similar issues. So and now comes generative modeling into the game. So generative modeling comes to rescue for this problem, and so I will now talk a bit more about generative modeling, and by this I will basically present the first surrogate model based on diffusion for CS physics. Are there questions until here? Because I think this is a good point to make a short break. Yeah, for sure, you can.
So just wondering, so when you present your units, more fancier version of unit, is that only for denoising, or is include already the prediction, or you just do the denoising and you do the prediction later?
No, so actually the results I've shown until now is not based. So it is a deterministic model without any denoising or something like this. So it just takes the initial conditions and predicts the conditions 12 hours later without any diffusion, any denoising in between. So it's
even the unit you show is not for denoising. It's just
until now, no.
Okay.
So until now it was just for deterministic forecast to get a proper baseline basically, which we want to achieve with our diffusion model.
And sorry, when you say 50 days, do you mean like several times of rollouts? Or
yeah, exactly. So to get the 50-day forecast, since it is trained for 12-hour forecast, this means I have 100 steps of rollout. Yeah, I think Balaji was the first one.
Tobias, okay, Balaji, okay.
Yes, hi. Thanks for this. So on the spectrum you showed, I had a question. So have you been following the work of Pedram Hassanzadeh, who was in the Data Wave project, has been doing a lot of work, and Ashish Chattopadhyay, they've been working on correcting spectral bias from deep learning.
Yeah.
Is that something that can be applied here?
Yes, for sure, it can be applied, and with that, this problem might be elevated. But I mean, so for sure, you could in some sense regularize your training of the neural network by adding some spectral loss. However, this would in some sense just solve the symptoms and not the issue itself in some sense.
That's a fair point. Yeah, thank you, Tobias.
Tobias, can I also have just a clarification? This is also, of course, large part apply also to the work of Charlotte. But I mean, when you use the forcing of 12 hours in the training, of course, this is, I mean, it's perfectly legitimate. But don't you think that the clarification is needed if you want to use then this model for predicting in operational mode, when you will never have those forcing a plus 12 hour at disposal?
So for sure, I wouldn't have the forcing coming from error 5 during forecasting or during operational forecasting, but we would have the operational forecast of the ECMWF or something like this, and then we can use it also as forcing.
Yeah. Okay. Yeah. Okay.
For sure, we would get errors on top of the current errors in some sense. But nevertheless, it should be also applicable to to atmospheric forecasts. I mean,
no, definitely, definitely. That's not sure. I was just thinking whether you had a clue on what will be the impact on the performance of the method when you feed it with a prediction rather than with an analysis. But anyway, this is just it's a detail. This is not the core of this talk.
Yep.
Julian?
Yes, very quick one. You answered it already, I think, but I'm not sure. So I ask again a very quick question. Is that an autoregressive model you use?
So yes, I use an autoregressive model, but this model is just so compared, for example, to GraphCast. I don't train with a rollout. I just train for the 12-hour forecast.
Yeah. Okay, and another quick one, I'm sorry, then maybe you can answer also later, is that you choose to put a transformer at the bottleneck of your unit. Could you comment on how important is it to have a transformer there? So is it data, does it change a lot or does it improve a lot your result, or would you have roughly the same thing with a basic unit?
So I would in the end get pretty similar results with our basic unit, I would guess. So in my preliminary tests, I had seen that if I replace in the bottleneck of the unit the convolution layers by a transformer, I get slightly better results. But it's yeah, I mean, let's say it's 5% difference or something like this. So it's not a huge difference, and I mean, this is also what I would say, what we see in for atmospheric surrogate models, that for sure the architecture might be in the end 5 to 10% or something like this, but the architecture doesn't matter so much, I would say.
Thank you.
Jiping?
Yes, Tobias, is a nice talk, and just a few questions about you mentioned the test period is 2 years, but
3 years, yes, yep.
Yeah, but the test you use 2015 as your model selection. What means model selection? How many model you have, and what difference?
So what I mean by model selection is that the neural network is optimized by reducing some loss function. So for example, in the case of the deterministic model, the mean squared error. And so what I mean by model selection is that let's say after each 500 iterations or something like this, training iterations, I then validate in the validation data set. And then in the end, after training, I select the model that has the lowest validation loss in what? That has the lowest loss in the validation data set. So this means that yeah, it is more by model selection, I mean that I basically select the best performing model in the validation data set, and basically in addition, for example, these experiments where I switch the bottleneck in the unit by a transformer, I just use the validation data set to verify this, because otherwise I would have a so-called data leakage. Meaning,
so in your testing period, you only use one model. Is it true?
Yeah, exactly. In my testing period, I just use one model that I have selected with my validation data set.
And have you tried use the high frequency forcing from ER5, or just use the after 12 hours forcing?
I selected this forcing, and specifically this forcing because the special thing about the 2 meter temperature, humidity, and the 10 meter wind speeds, and then every 12 hours, is that this data would be also available for the CMAC models. And so this means that if one would want to apply this for climate projections or something like this, it can be more or less directly applied. Whereas if you would use, let's say, hourly forcings and then more forcing variables, this forcing might be not available in other data sets. So yes, I mean, I would guess one could get better results if one would use more frequent forcings. But yeah, this is just the setting to, in some sense, to constrain to possibly other data sets.
So in your case, you didn't test it involved in more high frequency forcing.
No.
Okay.
I haven't tested
Thank you. Thank you.
I think we should go forward now, because it's very nice to have this interactive way, but we should also focus a bit on the main part. Thanks.
So as I said, generative modeling. So the main idea is that instead of just getting one single answer, one single forecast, the idea is to have a neural network that can generate many different samples. So a neural network that learns to sample from an unknown distribution, and which means then in the end, by giving one initial condition, the neural network would be then able to generate many different solutions. And so we have to do this in some sense because the smoothing issue is basically inherently coming from the use of a local Gaussian assumption, and we get then so-called double penalty effects, which then basically leads to these smoothing issues, to these unphysical issues. And so the idea here is to train a neural network as diffusion model. And so during training, we basically know our data. We know the target 4 and 12 hours. And in diffusion models, what we do is during training, we add noise to our data. And instead of adding noise just only once, we add noise many times until we have basically replaced all the information contained in our data by noise. And then a neural network is trained to take a noise field, to take the initial conditions, and then to revert this noising step, so to denoise for a small single step. And instead of training the neural network for just one noise amplitude, we train the neural network for all noise amplitudes. And then we can basically train the neural network by using a mean squared error loss between the added noise and what the neural network thinks. And then if we want to apply the neural network for forecasting, so if we now want to forecast with our neural network, we have our initial conditions and we want to reach the forecast. What we do then is we sample noise and then apply our neural network. And instead of applying our neural network just only once to denoise, we apply our neural network several times to denoise until our forecast. And so for this diffusion model, because the deterministic model can be in some sense seen as doing a similar thing like this in one step, and the diffusion model does this in many steps. And so this means the diffusion model is basically trained over many different noise amplitudes. And so in the end, I've chosen a bigger neural network for the diffusion model. So a neural network was up around 20, so 19.4 million parameters, so around 20 million parameters. So a much bigger neural network. And I basically achieved this by increasing the number of transformer layers in the bottleneck, and except this, the architecture between the deterministic model and the diffusion model is pretty similar. And then to basically generate the forecast, I do 20 sampling steps, and I use a second order sampler, and so it can be basically seen as integrating an ordinary differential equation, and so as integrating the ODE in pseudo time from time 1 to time 0, and here we can see that we have until time 0.5 a lot of noise in our data, and then we basically reduce the noise quite fast. So coming back to the results, if we now do this, so again, this is the normalized root square error over all model variables, then we can see that if we do a forecast with one single ensemble member, we are worse than the deterministic model, because the diffusion model suffers from double penalty issues, suffers from a double penalty in the normalized root square error. However, if we use 16 ensemble members and use the ensemble mean as forecast, then we can see that improve compared to the deterministic model by around 12%. And this again holds for all variables. And then if we now look into the smoothing, we can actually see that the diffusion model, so in the bottom row, keeps basically the sharpness of the neXtSIM simulations, and we can even here see that the field after 50 days resembles a bit the field as seen by neXtSIM. And then if we look into the energy spectrum, so one has to say again, I forgot to mention this, that this energy spectrum is an average across all 3 years in the testing data set. So it's not the energy spectrum of this snapshot, but of 3 years. And we can basically see that the diffusion model, that the generative model basically matches the energy spectrum as seen by neXtSIM.
Tobias, sorry, just a quick clarification. This is the energy spectra of the mean, or is the mean of the energy spectra of the individual realization?
It is the mean of the energy spectrum. So
okay.
It is the energy spectrum of single members, basically.
Yeah, okay. Okay, thanks.
So and now let's look a bit more into what the models see after this 50-day forecast. So in CIs, we basically know that if we have less CS, so if the CS concentration is lower, then CIs can be deformed there much more than for grid points or for cases where we have more CIs. And then also we can see, for example, here that these are then preferred regions where we have a change in the CS thickness. So this is the change in the CS thickness within 12 hours. And so we can see that if we have deformation there, so by divergence or convergence, we have then also a preferred change in the CS thickness there. For sure, we have also a lot of changes which seem to be unrelated to the deformation, but nevertheless there is some sort of a link between how the CS is deformed and the change in the CS thickness. So if we now look into what the deterministic model is saying, we can again really see that the deterministic model really smooths out everything, and we still see the link between the CS concentration and the deformation, and then also a much stronger link between the deformation and the CS thickness. However, it doesn't really look realistic. So it really seems really artificial. However, if we now use the generative diffusion model, we can actually see that the generative diffusion model generates fields that represent these physical consistent links basically, and then also in the change of the CS thickness, we can see that the fields look very similar, in fact. And so what we then can do is actually we can look into the distribution of the deformation. And so here I show the shear deformation and the total deformation. And so this is the empirical density. And so in black is what neXtSIM sees. In blue is what the deterministic model sees. So we see that the deterministic model is quite off. Also for the high shear values and the high total deformation values. And then in red we see what the generative diffusion model says, and we can basically see that the diffusion model more or less matches in the high values the distribution of neXtSIM, whereas in the low deformation values we have less pixels with low deformation than in neXtSIM. But nevertheless, what really matters here is that we more or less match the distribution of the high deformation values. And so based on this, so we can then measure how much the distribution changes, or how much the moments of the distribution change if we coarse grain our data, and this gives us then in some sense an indicator of the multifractality of the field. And so again, here in black we see neXtSIM in red the diffusion model, and blue the deterministic model. And here I show how much the logarithmic scaling of the first moment of the distribution, of the second moment, and of the third moment. And if it is multifractal, we basically expect a polar behavior, and this is basically what we see here. And again, we can basically see that if we derive spatial scaling laws from the predicted fields of our diffusion model, these scaling laws are pretty similar to the scaling laws as derived by neXtSIM. And the deterministic model is much more flat in some sense, which means that the deterministic model resembles a bit what a CS model with our VP, so with a viscous plastic rheology would say. So and then we can also analyze the temporal behavior. So here I show the 90th percentile of the shear for the 50-day forecast that I've shown here earlier. And so the black line is the 90th percentile of neXtSIM. And so if we now plot the deterministic model, we see again that the deterministic model has a bias compared to neXtSIM in the 90th percentile. And so if we now plot in what the diffusion model sees, we see that the diffusion model does a pretty good job, especially in the first 1.5 weeks. And then afterwards the trajectories of neXtSIM and of the diffusion model diverge. But nevertheless, for example, here we have a strong wind event, a cyclone, I think, moving through, and we can see that the diffusion model gives pretty realistic results. And so this basically means that the diffusion model also has a similar temporal behavior as neXtSIM. So, and then the last thing what I did is we can then apply this model also for idealized cases. So here I have an idealized case inspired by the benchmark case from Caroline Mielman, where we have a cyclone moving from the lower left to the upper right. And so in the left I show the CS thickness, the CS concentration, the CS speed, and then the divergence, the shear, and the deformation. And if we now start the movie, we can see so if we compare this to for example what CS cube with our brittle rheology says for this case, it gives pretty realistic looking results. And yeah, so it seems like despite the fact that the model has never seen such an idealized case, so it was trained on real simulation data, it also works for these idealized cases. So yeah, today I've spoken about generative diffusion for CS physics. The first thing I've shown to you is that this unlocks an improved data-driven modeling compared to deterministic modeling. Then what I've also seen is that we can actually train such a diffusion model also for model error corrections. Then the second thing is what I've shown is that these diffusion models resolve the issues with deterministic surrogate modeling, and they maintain the sharpness of the targeted data. Then also I've shown to you that the model exhibits physical consistent forecasts, so we can really see the links between different variables in the forecast. And this is not for sure. It is also possible with the deterministic model, but not as nicely as with the diffusion model. And the scaling laws we can the then derived scaling laws are similar to those derived from neXtSIM. And so the next steps is to use latent diffusion to basically scale this up for an Arctic-wide setup, and then also to basically train a neural network to take physical bounds into account. Because here the neural network is just trained with a mean squared error loss, which means that physical bound, for example, that the CS thickness can be not negative. Well, has to be always has to be always positive or zero. It's not taken into account during the training. So we submitted a paper to James. So this is the link to the paper. Since today is also the preprint is available since today or since this morning, and then you have also the QR code to the code of the models. And with that, I would be finished. And yeah, do we have questions or discussion points?
Okay, thank you very much, Tobias. I think it was Julien first, and then Ali, and then we'll see. Julien, please.
Yeah, thank you very much. It's a very nice work. I really like it. I have two very quick questions. So you show that you can do ensemble forecast with your model, but if you want to have if you want to, after two time step, for example, if you have to have an ensemble of 16, you can either do 4 members at the first time step, and then takes each of these 4 members as initial condition and takes 4 members at the second time step, or do 1 member as in 16, or do 8 and then 2. So is it important how you construct this ensemble or not? So that's my first question. And my second question is more technical, is how do you specify your initial condition to the your conditioning to the model? Is that, do you stack it with a noisy image, or is that another way?
So I will first answer the second question. So I basically stuck it with the noisy image.
Okay.
So
perfect.
And because the first question is a bit more needs possibly a bit more discussion. So what I basically do, I predict directly 16 ensemble members and then use the 16 ensemble members all the way. So which means that the 16 ensemble members start with the same initial conditions, and then I basically replicate the initial condition 16 times, and since the model is inherently stochastic, this means that even if I start with the same initial conditions, I get 16 different forecasts, and then I basically propagate in time like it is a deterministic or
Okay, so the ensemble part is only for the first time step. Then you just have one initial condition for one forecast after the first time step.
Exactly, because you can basically see it like I do a Monte Carlo sample from the distribution.
Yeah, but you can Monte Carlo also later on. So did you try, for example, to do an ensemble for the last time step of your forecast, or did you play with this and did you see some effect? No, okay.
I haven't.
Okay.
Ali?
Because okay.
Sorry.
Okay.
No, if you want to finish, Tobias, please complete, of course. I mean, it's up to you.
I think you can only do it for the first time step because the diffusion model is trained for a 12-hour forecast. So which means that the diffusion model is trained for the first 12-hour basically, and not for the last 12 hours. And so if you would apply your diffusion model, so let's say you would do our deterministic forecast up to 15 days and then apply your diffusion model on top of this, the diffusion model wouldn't give you a proper ensemble.
No, I also use the diffusion model with one member, but okay, I don't want to yeah.
Ali, please.
thank you. Thanks, Tobias. I don't have to say this is very impressive anyway, but maybe my question is now a bit more unclear to me, because I was going to ask if there's a way to look at the ensemble spread somehow in order to I mean, mostly asking for DA purposes, but
yeah. So I mean, the diffusion model is more or less trained to basically minimize the maximum likelihood of a predicted ensemble, if you want to say so. However, what I've seen is that here I show the spread skill ratio for the CS thickness and for the CS velocity. So forget about this yellow line. Just concentrate on the diffusion line here, and we can basically see that for the CS thickness, the spread skill ratio is quite good initially, and then it gets worse. This is because of the dissipative behavior of CS. So this has the same reasoning as seen by Yu Meng. If you basically perturb the initial conditions, then the memory is lost after, let's say, 2 weeks or something like this, because CS is heavily driven by forcings. So, however, for the CS velocities, we can see that the spread skill ratio is quite bad. Meaning that the diffusion model is heavily underdispersive. And frankly, I don't know why. It shouldn't be like this. So for the velocities, it should look like for the CS thickness, because here I show the rank histogram after 12 hours and the rank histogram after 10 days, and for the CS thickness we see that it is more or less a perfect rank histogram, whereas for the CS velocities it looks horrible. And what I guess at the moment is that there is some sort of distribution shift from the training data compared to the validation testing data. But yeah, I have to investigate this more and to see why this happens, because yeah, diffusion models are supposed to give a more or less calibrated ensemble. Well, I mean, they are not trained to do so, but implicitly by doing this maximum likelihood approach, you basically also tune your ensemble spread.
Okay, thank you.
There have been let's take the question from Chris, and then we can come back to the points raised by Julian on the chat. Chris, please.
Yeah, I think this probably follows up with what other people are asking. I guess one of the use cases for these kind of emulators essentially is to be able to run large ensembles into the future with climate forcing. Given that we're not even sure necessarily that neXtSIM generalizes well to future climates, how do you feel about that prospect using one of these diffusion models? I mean, in terms of generalization, how do you propose to test that or examine the future uses of this kind of tool?
I mean, one could try to basically validate against observations for sure. Or I mean, what I actually thought about is, for example, if I train now for the full Arctic setup, if this model can be then applied to Antarctica, for example, and if it can be applied, or I mean, if it gives results that are not so bad, let's say it this way, for sure, it is no guarantee that it works also for future climates, but one could also test by using climate forcings and then to see what if the results one gets are similar to basically what other climate model says. But yeah, I would say there's no guarantee that this generalizes to future climates. However, since I've seen this idealized test case, and that it seems to generalize to this idealized test case. I'm actually quite optimistic that it might also work for different climate settings. But yeah, I don't know.
There was Julian who said that could this drift of accuracy over time be due to what we were discussing, that you sample an ensemble only for the first time step? This.
But so.
Are you reading the?
I'm just thinking about an answer because so I would say the diffusion model is basically trained to represent the uncertainty what we would expect getting after 12 hours. So this means if we cycle then the diffusion model. So let's say in the first few iterations, we have a more or less linearly increase of the uncertainties or exponential increase. That if the uncertainty of previous time steps is damped by the dissipation of the system, then this means that the whole uncertainty of the forecast is lower than it should be. I mean, so. I hope what's this?
But what I mean is that for the second time step, when you cycle your model, you have the uncertainty due to the model error that is well sampled by the diffusion model, as you said, because it's supposed to sample well the uncertainty after 12 hours. But you should also account for the uncertainty of the initial condition that you have after 12 hours that is greater than for the initial time. So you should have the uncertainty that increase with time.
Yeah, so I totally agree with you that the diffusion model is certainly not taking the uncertainty in the initial conditions into account. But the problem with diffusion models or with training diffusion models is that one could take this into account by doing some sort of rollouts during training. Like done in GraphCast or something like this. But the problem with that is that it is not so trivial to basically extend the training of the diffusion model for rollouts like this.
Yeah, I agree.
It is also true that because of the fact that it's not describing the error in the initial condition, the use of these for running an ensemble of prediction aimed at a probabilistic forecast with this different initial condition or with the same model, it is of course limited. Having said that, of course, ensemble prediction for a lot of systems, including CIs, will include perturbing forcing or parameter, which precisely entail about exploring different models and selecting the best. But I think it's important to distinguish these things because in the atmosphere, for instance, of course, ensemble prediction is designed to catch the probabilistic forecast due to error in initial condition. But anyway, this is a clarification in relation to what Chris was saying earlier.
I agree with that.
Yeah, but it's interesting because, for example, in GenCast, so which is a generative also emulator of the weather forecast, they show that they are very reliable, despite the fact that they don't account for initial condition errors or initial condition uncertainty. So this is something that always sounds weird to me, but.
No, it depends. It depends. It depends. Sorry, Tobias, it's your fault. It's your fault.
I possibly wanted to say exactly the same as you, Alberto, that the atmosphere is not as dissipative as sea ice. So meaning the atmosphere is not really driven by any external forcings. And here, I mean, as I designed the setup, it's really just driven by external forcings, and I mean even the lateral conditions are not given. And yeah.
Yeah, but I think Julien, I think you were saying the opposite. Julien was saying that in a context like the atmosphere, GenCast was showing that they were doing successfully prediction with generative model, despite of the fact that we would have expected their initial condition error to be predominant. That's what you were saying, right, Julien?
Predominant, I don't know, but present.
Yeah,
at
but
least,
I think, I mean, I don't know the resolution of what you're talking about, but again, even 12-hour horizon, if you're talking about 500 hectopascal, the error in the 500 hectopascal at the resolution which is a synoptic one, again, you are probably not settling ourselves in a situation in which initial condition error is so explosive. It will not be the same for a convective resolving model of the atmosphere, probably. But anyway, this is just a
yeah. No, but precisely if your uncertainty depends. Sorry, I don't want to steal the. So it's my last intervention. But if your uncertainty depends on the forcing, it's an additional reason to at each time step generate an ensemble. So for your first time step, you generate an ensemble, let's say of 10 members, and then you take each of these 10 members, and from each of these 10 members, you can generate a new ensemble, etc., etc.
Sure.
And this one, maybe you have more chance to have to be reliable. That would be my guess. But
I see. Yeah. I see what you mean, and yes, certainly. But I mean, yeah, I would say I would argue how I have done it. It's also a more or less valid a Monte Carlo sample from the probability distribution.
Yeah, true.
Yeah, by the way, I think this all is assuming, sorry, this is a very final, purely formal clarification, but this is for my own understanding. All of this, Tobias, is done under the assumption that you assume that it exists any distribution on some attractor of this model. I mean, I think it's a sort of underlying assumption over there, right?
I mean, the thing is that the generative model itself assumes no distribution at all. Meaning that it, yeah. But I agree with you that one can see it like, then hopefully something from the attractor somehow. Yeah.
Okay, I think we should close here, and right, and I don't see any more raised hands. Thank you very much, Tobias. It's been your excellent work, and also let me say excellent presentation. Very, very clear and very inspiring. Okay, so we will all probably next. I don't know. I don't remember, Solène, if there is a next webinar already scheduled. If you're still there, Solène or Pierre, you can maybe remind that.
Yes, next month it will be with Robert Gendersey from Germany.
Wonderful. Okay. Okay. Thank you very much. Ciao.
Thanks. Bye.
Ciao.
Bye.
Ciao.